Hi everyone, thanks for joining today. We're joined by Peter Lawrey, who's Director of Chronicle Software, and he'll be talking about pragmatic programming on low latency systems. Any questions you have, if you can put on the chat box just to the right of your screen, and then myself or Peter will ask the questions, and obviously Peter will answer themselves. So any questions, let's wait till the end after Peter's talk, and then we can take it from there. But Peter, I'll pass across to you now, and everyone enjoy. Thanks.
Well, good afternoon, everyone. Today I'm giving a talk I recently gave in Shanghai last year for the lockdown, obviously, and I think it went down pretty well. So hopefully everyone will be able to get something from it. It's targeted both at beginners to programming, but hopefully also has something in there for more advanced developers with a lot of experience. So who am I? I'm a Java champion. I've got the most answers in the world for Java and the JVM on Stack Overflow. Software I wrote, the open source software I wrote, got downloaded 18 million times a couple of years ago. And as a company, most of the our clients are tier 1 banks. So when I started programming, I was only 14, and this was my first computer, and it ran at a true 5 megahertz, which meant it was faster than a PC, which only ran at 4.77 megahertz. It had 128 kilobytes of memory, and I never used it all. I never found a use for all 128 kilobytes. The keyboard alone, to replace it, cost $2,000 at the time, which obviously is worth even more now. Now, when it came to replacing it or upgrading it after a chip died, I got another base unit from someone else who was selling their computer secondhand, and they had a PhD in psychology. And I was wondering why it was this person had a computer and he was teaching himself to program. So I asked him why he was doing that, and he said, well, computers are easier to fix than people. So even though he had a PhD in psychology, he was retraining as a software developer. And I found that that's true even now, especially as you become more experienced and you can find the technical issues less challenging, especially if you stay within your specialty. You always find, though, that the hardest problems are people problems, because people are harder to solve. So one of the things that struck me sort of somewhat through my career, this is after I'd been developing for quite some time, as I came to realize that developers don't actually spend most of their time writing code. That's generally the perception. And certainly junior developers tend to measure their productivity in terms of how many lines of code they added. But I found the more senior developers tend to measure their productivity in how many lines of code they removed, rather than how much they added. And nevertheless, I did as an exercise once to just compare IDEs. I printed out some classes I did that were in a very productive day. I'd written 700 lines of code, and I thought that was a good amount of coding for that day. And so after printing it out, I typed it in again using a couple of different IDEs, and both times it only took me 10%, about 50 minutes, to write that code again from scratch from a printout. So I'd only spent, even in a very productive day, only about 10% of my time writing the code, and the rest of the time was actually spent understanding the problem, which is what developers spend most of their time doing. So it's certainly a myth that, and that's developers who get to spend most of their time solving problems. A lot of developers actually spend their time either trying to fix problems or trying to gather requirements. which is also a fairly significant portion of any project, is extracting the requirements, clarifying them, writing the documentation, and fixing issues. And then you're spending even less time actually writing new code that will end up in production. So when I graduated from university, one of the things I remember them saying was that that 30% of the graduates would be working in an industry that didn't exist within 10 years. And obviously that sort of comes as a curious comment, you know, sort of wondering, well, what does that mean? What would I be doing then? But it turned out to be true, because within 10 years, I was working with World Wide Web, Java, algorithmic trading, and none of those existed when I graduated. Java hadn't been released. There was no World Wide Web. And if you think about how much the industry has changed in the last 10 years, it's reasonable to assume it will change just as much in the next 10 years. And you may actually be doing a job, there's a good chance you'll be doing a job that just doesn't even exist yet, something that nobody does today. So one of the things to remember is the importance of effective communication. So a recurring thing I've seen in my career is actually communicating what's been done. So first, extracting the requirements, what actually needs to be done, making sure that that's clear and that it's understood that that's what needs to happen. I worked on a project once that got canned after 9 months because it turned out that through some sort of miscommunication, the users didn't actually want it. So they'd spent 9 months, 6 developers, 6 contractors, and when they came to testing it, turned out that nobody wanted to do the testing because nobody actually wanted the functionality. And then there's the other side. Once you've developed it, make sure that it's communicated that why this was done, how to use it, and so on. A similar project, a similar interesting project I had was, I was given the task once to tune a trading system with 2 main constraints, as they couldn't change either the hardware or the software. So I thought this would be an interesting challenge. How do you improve the performance without actually changing either of those 2 things? And is that even possible? Well, it turned out it was, because the first thing I did was investigate, well, where were the delays? And each time I found a delay and a cause, it was obvious that what we really needed was a component that did a particular thing. And it turned out someone had already written that, but it wasn't being used because it wasn't clear as to, no one had thought it was worth the risk switching to this new implementation. In some cases, these were implementations that had been there for 3 years. No one had thought that it was worth switching to it because they couldn't show why would you use this new implementation rather than the one that already works. So by showing, well, we have this problem, that if you use this other implementation, the problem goes away. We were able to tune the system significantly, and we reduced the 3 nines by a factor of 25. So the worst one, 1,000, dropped by a factor of 25. And that was remarkable, partly because, like I said, I only ended up using software that had already been written and using the existing hardware. We did it all within 6 weeks from when we started to when it was in production. Another thing is make sure that people know how to use it and know what it is. I've done a number of projects where I developed something cool, it's very useful. I know it's useful because it was eventually used, but it took a long time to be picked up because either people didn't know it was there, or they didn't understand it, or the right people didn't realize it was available. And in some cases, it was years later when this project was eventually picked up and used, because it took that long to find the right person who actually wanted to use it. So another way around this is to actually have documentation-driven development, where you start with, well, you start with the piece you know is the most essential to get right, such as documentation. You write the documentation first, at least conceptually, you write the documentation first, and then you do the implementation, though of course you may use test-driven development as the next step. So you do the documentation, then write the tests, then write the implementation. That's all very well and good, but the reality is that what you find is that it's only possible to do that when you understand the problem really well. The reality is that someone who's capable of doing that has actually written many implementations, done a lot of prototyping previously, worked on many implementations first, maybe written some tests first, and then in the next iteration, they are able to write the documentation first, then they're able to write the tests, and then they'll write the implementation. It's not possible to do that when you don't understand the problem or the nature of it. I think that's what I talked. Public speaking turned out to be far more important than I imagined. I avoided public speaking for the first 10 years of my career. I didn't do it at university, and I didn't do it in my job until eventually I had a pre-sales role, and essentially I was forced to do it. And now I it used to terrify me, and now I really enjoy it. And found that it really helped my career in general. Again, it's about communicating, and it's partly about getting your name out there as well. But yeah, public speaking, it was an essential part of my career development. And that's something that took me a long time to realize. As I mentioned earlier, senior developers tend to more measure like how can I simplify the code and make it more maintainable, and yet it still does everything. It still does all the same things. Yeah, another thing it took me a long time to realize is the importance of exercise. Again, this is something I certainly avoided in high school, and it didn't do at all at university. But then, as I got older, I realized that having some regular exercise of at least 30 minutes really does help both your stress levels, but also your mental concentration, and you'll end up being more productive. Be more productive, but more efficient in terms of what you deliver. Now, one of the things to watch out for, and this is another difference between, say, junior developers and more senior developers, is developers love solving problems, whether they need to be solved or not. And you find that junior developers go around solving lots of problems, and they're more productive. They go and solve more problems. The problem is that a lot of those problems weren't problems that needed to be solved. And what you find with more senior developers is they'll stand back and say, well, what's the actual requirement here? And what is the best solution to fit that requirement? Rather than let's create a solution looking for a problem to solve. Once you've done that many times, you've done many implementations, and you've done the same thing 3 or 4 different ways already in your career, you tend more to sit back and say, well, which one do I actually need to be using? What's the best way of doing this based on what I've done before? Another key principle which comes up again and again is you ain't going to need it. And this is still an issue for me. I'm still one of these people that love solving problems, even if they don't need to be solved. And so you need to remind myself that you really just need to focus on what are the actual requirements first. Do exactly what's needed first, then the solution will be simpler and easier to maintain in the long run. Adding functionality that you imagine being useful generally leads to regret at some point. And a principle I quite like is actually the comparison of wet versus dry. So one of the beauties of dry is that you can reduce the amount of code, and if you use the appropriate abstraction, you can reduce a lot of duplication and maintenance overhead. The problem is that if you take this too far, then you end up making your code so abstract that it becomes really difficult to maintain and difficult for anyone else to understand. Well, what is it actually doing? Because you've, I don't know, you've decided that 1 is a constant, and then you've gone and put 1 as a variable somewhere, and that way 1 doesn't get repeated throughout your code. It's just not really a useful way of reducing duplication. What you actually want to do is you want to allow a certain amount of duplication, and this tends to happen more in unit tests. So some of the programming paradigms, such as dry and trying to make your code really concise, makes more and clean, tends to be more important for production code than it is for test code. Test code, you actually want to do some of the things that you probably shouldn't be doing. Repeating yourself to make each test quite independent. You don't want to go crazy, but it's less important. And sometimes it's desirable to do things in unit tests that you wouldn't want to be doing in production code. So the difference that I see between junior and senior developers is that a junior developer can take a simple problem and build a really complex system. Building a complex system is actually quite easy. What you really want to do is take a complex problem and produce a simple solution to a complex problem. And that's the hard bit, is producing simple, elegant solutions is a lot harder than producing complex ones. And that takes a lot of experience and a lot of time and a lot more effort to produce a simple solution. But that's one of the measures I find is the elegance of the solution, how simple it is for what is potentially quite a complex problem. Another thing is to make sure that you've got your separations of concern right, and having your right levels of abstraction and separation between different components. And one of the methodologies which is useful for that is around microservices, trying to having clear separation between different components and functionality. And this can have two benefits. You may want to separate microservices for a technical reason, which is having clear contracts, easy to test, easier to deploy. But you also may have it just for organizational reasons, and this can also mean that your design can either match a more technical layout where the separations are technical, or it may actually more reflect your organizational chart where different teams or individuals within teams are responsible for separate microservices, and that can I've seen both work reasonably well, and microservices can be very useful if you've got two very strong developers that don't see eye to eye, because you can set up a contract between them and say, well, this is the bit you both need to work to. You can go and implement your individual services how you think is most appropriate for that piece of functionality. So one of the things that is also important for maintainability is avoiding premature optimization. I've seen many examples where trying to put in clever code actually doesn't help or actually makes things worse. Part of the reason why being clever can make things worse is that the JVM has like a playbook or a cookbook of optimization. So it'll recognize a pattern and it'll say, for this pattern, I will generate this code. And for this pattern, I generate this code. If you write creative code or clever code, it may not fit any particular pattern or not fit it particularly well, and it'll end up generating code that's less efficient than what it would have done if you just made it really simple. So it's often, I mean, the most important thing for a program is to be correct. So it doesn't matter how fast you dig a hole or how big you dig the hole. If you're digging the hole in the wrong place, it doesn't really matter. You need to make sure your program is correct, that the holes are in the right place. Then you can worry about, well, how quickly can I do this and how efficiently can I do it? almost always correctness comes first. The only exception I can think of is when it comes down to things like monitoring. If you want to monitor the performance of an application, the more accurate you make it, the more you disturb the application, which then actually makes the monitoring less accurate. So you want to have a very lightweight monitoring of your application, and you're better off having something that's a little bit incorrect than attempting to make it really correct and then actually disturbing the application and being incorrect anyway. So I think performance monitoring is about the only exception where optimization is perhaps more important than strictly being correct. But for the most part, optimization should come after you have something correct. You've got a realistic working example, and then you look, well, this is how the code should be written, or these bits need to be optimized. So yeah, instead of having a code clever, make it clean, easy to understand, and then the JVM's got a good chance of being able to optimize it efficiently as well. Another important thing to remember is that if you write clever code that's difficult to understand, you can find that someone in 6 months' time read the code and can find it very confusing, and that will either slow them down or actually introduce an error, try to change it because you made some brittle assumptions, and that person could be you. There's many times when I've looked back at code, maybe not 6 months, but certainly years ago, and I look at it and I just shake my head, and I just can't believe that I left code like that, because coming back to it now, it just looks terrible. And then, so that's why you know, it is worth making the effort to make your code maintainable and easy to use, easy to change later. Another thing to remember is that code is read much more times than you write it. So while you might spend a small amount of time writing code, you will someone will later read that code, and someone else will probably read that code. Chances are that code can be read 3 or 5 times more, can be read 3 to 5 times, even though it was written once. So writing code to be easy to be read is much more important than how fast it is to write the code in the first place. So again, some developers will focus on how quickly they can write the code. And that was never really important in the first place, but it's how easily it can be read and understood that is far more important. Another key principle is being able to detect and fix bugs sooner, as soon as you make them, reduces the cost of those bugs. So the longer it stays in your code, the longer it is between when you made the bug and when you detected it, the higher the cost. And I mean, this chart is just an example, but certainly the cost of some bugs can be well over 30 times the cost of if you just fixed it really quickly and made sure it didn't happen in the first place. So it is important to detect and fix, come up with mechanisms for detecting and fixing bugs as early in the development life cycle as possible. And some effort should go into making sure that you're using that approach and you're supporting that approach. So as I mentioned before, there's lots of different kinds of driven development. What some I left off is like CV driven development, where you're doing development that's going to look good on your CV, or mortgage driven development, which is just things that are just going to help you pay the mortgage. But some of the better approach is to focus on these styles, such as documentation or test-driven development. They're not easy, particularly if it's an area, like I said before, an area that you're not familiar with. It's very hard to know in advance what it is that you need to do if you're not familiar with the problem space or the technology. So it's often to actually achieve this, you often need to start with some prototypes and prototype-driven development, or someone has to, or they need to have done prototypes before, maybe in a previous project. Then they can go on. I'll start with test-driven development. But they can only do that because they've got a lot of experience. So if you take these approaches and then find that actually it just doesn't seem to be working for you, it's possible that you just don't understand the problem well enough, and you shouldn't be trying this yet first. You should be trying perhaps some prototyping, trying out some different ideas, but then allow time to do a cycle. Maybe you won't get to do it before it goes into production. But what you do want to aim for is to be able to do a cycle where you actually start more with focusing on the models and the documentation, the tests, and then do the development that reflects those rather than the other way around. Yes, so driven development is a lot easier if you've got experience. Otherwise, you may find that you really just have to start with prototypes. So an example was a project I did to do with a high throughput blockchain. I'd done test-driven development, behavior-driven development for some time, and in fact, I've actually written a framework for behavior-driven development. So I'm a big advocate of it. But then when I came to do Descended, I found it just wasn't appropriate. It just didn't work. And that's because I just didn't understand the space well enough. I had to create prototypes. I had to create a first iteration. And in fact, it had a different name. I had to create a first iteration. Only after having that iteration and seeing how it worked and understanding the problem and the technologies involved, then I could go back and work out how to do the behavior-driven development. And then I basically did a rewrite based on the behavior-driven development afterwards. So one of the dangers that often happens with prototypes is that they say, well, you've sort of got basically something working, let's just productionize it. And that's really a good idea unless time to market is really sensitive and you really don't, the quality isn't important. What you really want to do is you should always plan that if you're going to do any prototype, that you are going to do a rewrite, ideally within the time frame. So you should try and get your prototypes done no more than about a third to a half of the life of the project that you're going to do that functionality. You want to stop prototyping at a certain, be able to plan to stop prototyping at a certain point, then rewrite it, redo it properly. Now that you know what you know from playing with the prototypes. So starting to go into the low latency space, which is more my specialty, which is low latency Java and trading systems. One of the things to realize in low latency is that you're driving data at much higher rates than you would need to deliver to a human. So humans can be quite tolerant of what for a computer is an eternity. If you're watching a cinema, although not as many people are these days, then it's the video is typically at about 24 hertz, which is kind of slow by modern standards, but a lot of movies are still at 24 hertz, and that means there's actually 42 milliseconds between frames. You can't see that. Apparently, there are some people who can find watching movies annoying, but most people can't even see less than 42 milliseconds. They just will not notice the difference. So any kind of delay that adds up to less than 42 milliseconds for data being presented to a human really doesn't matter. It's just not going to make a difference. However, when you look at how websites actually work, they usually go into the hundreds of milliseconds, maybe 200, 300 milliseconds is considered acceptable for a non-trivial request. So then that's okay, but you will notice the difference, but it doesn't necessarily matter. However, for trading systems, there's a much higher expectation, and certainly one of the highest market data feeds that I've come across is Opera, which is options market data in Chicago. And that can see peaks of nearly 1 million messages in 10 milliseconds. So you can get so it's still not quite. So this is a cross between low latency and high throughput. So it's very high throughput, and it has latency requirements lower than what you can see, but you can handle very high bursts of data, and that the sort of system you designed for there is quite different than the sort of system that you would present to a human. And obviously this sort of data needs to be throttled if you're going to be displaying it. So low latency means different things in different contexts. So certainly for people who are used to batch, particularly overnight batch, the next step is, can we get a report in an hour? So obviously an hour is a lot less than waiting a whole day or overnight. So then that's considered an improvement. Don't necessarily call that low latency, but certainly that's enough. That's real time for them, real time enough. And then it tends to be in our spaces where they're starting to get into sub-second. And certainly most clients want to be less than a millisecond most of the time. They will accept delays over a millisecond some of the time, but essentially they care about latencies faster than you can see. That latencies faster than you can see will cost them money. And they can often put an estimate of like a dollar figure as to how much over time a delay will cost them. And then sort of on the far end of the scale, certainly for Java, is that you're getting into the single-digit microseconds. That's about as far as Java will go. You can get better results in C++, but really if you're going to that next level, you're talking about hardware like FPGA rather than in code. So back to my point about microservices, is that people and software can work together when there's clear separation of concern and contracts, and then microservices can really help with that. So the key part, of course, with microservices is your messaging needs to be fast enough. So obviously adding this separation between components means that you're adding an overhead of the messaging between your services, so you're marshalling data, passing the messages around and so on. But as long as your messaging infrastructure is fast enough, that won't necessarily add a significant problem. And in fact, we've come across situations where adding the messaging sped things up, because now you could have two processes running at the same time, two services running concurrently, right? Whereas before they weren't running concurrently, and you didn't. So you had access to more processing power. And certainly one of the trends that we're seeing is that we're getting CPUs with sockets with a lot more CPUs. Ryzen, for example, have a single socket which now supports 64 cores. So how do you access the cores? Well, one of the ways of doing that is to have more microservices running simultaneously. So that uses more processing power, but you've got available processing power to use. In our case, another thing is we record every message in Chronicle. So by recording every message, you can see all the messages that are going through, and you can improve the efficiency of those messages. Maybe they don't have to send as much data. Maybe certain messages don't need to be sent. And by doing that, they can cut down the interchange between components and also speed things up. So you generally advocate a Lambda architecture, which is very easy to compose and to test. It takes a certain kind of mindset, and like I said, this is kind of more useful for real time and low latency, because that's the focus of what you're trying to achieve. So you take an event source, which is an ever-growing, immutable queue of events. You run it through a function and you produce outcomes. Now, this is this is very easy to test, but is limited because it doesn't have state. So it tends to work well for gateways where you're normalizing messages from external sources and normalizing them to be sent out. However, if you've got something like an order manager or something that's processing market data, you also want to have state. And so the way we get around that is that we say conceptually, this is a function which is a result of every event it's ever seen. And the state is essentially a cache of the useful data to make that more efficient and practical. And these can be chained together. So you've got normalizing at the gateways at the sides, and internally you've got some sort of state machine. Now, the nice thing about this approach is that that control system in the middle, which is the most complicated part, can be tested using just the inbound messages. None of the other components even need to be running. You don't need access to them. You don't need access to some external database, which may be in some state. You can easily reproduce the functionality and test it in a deterministic manner using just the inbound messages. And that makes it very easy to test standalone. And this is proven to be a very useful programming model that scales quite nicely, both organizationally and in terms of performance. So I meant to change those numbers. This was from last year. The prices have got nearly 20% cheaper now. So, so one of the things that's been continuing to change is that high performance storage is getting cheaper. These things, each card can handle about 2 gigabytes a second write speed, and you can have terabytes of data, enterprise grade data for very little money. And this kind of trend means that storing everything for your event sources is very practical. And this is the sort of thing you tended to avoid in the past, but now we can just record everything going through every microservice so we've got complete tracing and logging, deterministic logging. Okay, so let's come on to the questions bit.
Yeah, hey Peter. So thanks for that. Anyone who's obviously got a question, if you could just type it now in the chat box on the right, and then I can ask Peter, and then he can get them answered. But thanks very much for that, Peter. That was really interesting.
No worries.
So yeah, first question from Mahmood. I think you can see it as well, Peter. Could you tell us about the most difficult / memorable bug you've had to solve?
Okay. So one bug that tends to strike me was so one of the things that we do with Java is we use it in ways that it clearly was never intended, and that is to have low-level memory access to raw memory. So so two of the main data structures we use for Q and map actually use directly access physical memory through memory mapped files. And Java is just not designed for that. So we've used a special class called unsafe, which they don't recommend you use, but we used it anyway because there really is no alternative. So because we're accessing the raw memory directly, we come across issues in terms of how the CPUs themselves function, rather than this sort of idealized virtual machine. And we found this bug where memory was being corrupted somewhat randomly in this off-heap data that's just obviously Java has no support for. It can't even see what's there. The debuggers have no idea. And eventually traced it down to, it turned out that we were using, we were trying to do a thread safe operation, which is called a CAS, compare and set operation. And Intel allows you to attempt to do a CAS across cache lines. So the CPU caches in the cache in your CPU is broken up into 64-byte cache lines. And if you do a thread safe operation like volatile or CAS on inside a cache line in Intel, it works fine. However, if you do the same operation but across cache lines, then it works most of the time, but not always. So at about in some tests about 1 in 100,000, maybe 1 in a million times, you'll find that the operation isn't actually atomic, even though it should be, and which is very difficult to trace in Java, not surprisingly. It took me ages to even figure out what could be causing the problem, but later realized that attempting to do thread-safe operations across cache lines should really have expected that was never going to work, and certainly it doesn't.
Cool, perfect. Thanks, Peter. Next question is from Jan. Sorry, Scott. Can you tell us what? Sorry, actually, there's one question before that. Any good books / resources about high performance Java that you could recommend to everyone?
Yeah, Brian Gertzen's got a good book on concurrency, and I think that's one of the best technical books for Java I've ever come across. Concurrency in practice. There really isn't a lot of good books. I think mostly because in the high performance space, it's a bit specialized, and I haven't found anyone who does that is also willing to write a book. I did look at doing it myself, but you get kudos, but you get it just doesn't make sense commercially. To write a book, it takes about 6 to 9 months full time, and it will take longer than that in terms of elapsed time. And at the end of it, it will certainly raise your profile, but won't necessarily. You have to be very lucky that you would actually cover the cost of the time you spent doing it. So that's why probably less people, get more people writing these books. What you will find though is different blogs. So obviously I have a blog. Martin Thompson has a blog, which is excellent. Gil Tene, who is the CTO of Azul, I highly recommend you have a look at his videos on performance Java. So it's really about video, and blog content is probably the main route to get picking up some of these skills. And obviously I'm doing more videos, so watch out.
Yeah. Perfect. Thanks, Peter. Next question. Could you tell us what are the main JVM low latency principles, and maybe some tips and tricks along with that as well?
The main principles that we come across is create less objects. Even though creating objects is cheap, certainly cheaper than it was from previous versions of Java, creating less objects still creates less churn, less overhead on the CPU. Allocation is still surprisingly expensive when you have a look at the high percentiles, and that's because if you're creating a lot of garbage, then you're essentially you're filling up your caches with garbage and pushing useful data out of your caches, and then that means there's delays when you actually go back to get that data. So I wouldn't. So looking at techniques for reducing the amount of allocation. The JVM helps you a little bit. It's called object elation. I'm trying to remember the exact term, but essentially what it does is the JVM can work out that some objects are short-lived and don't need to be created, and it'll essentially put the fields of the object into the stack. So that can work very nicely when it works. Unfortunately, it doesn't work consistently, and it can just stop working for no apparent reason, because it's a bit of an art. And by stop working, I mean while the program's running. So it could work for a period of time, and I've seen it actually stop working because it's re-optimized the code and it wasn't able to work out that object wasn't needed anymore. So it's very cool, but it is surprisingly unreliable.
Cool. Thanks, Peter. Next question is, what is mechanical sympathy and how one can learn it?
Okay, so mechanical sympathy is being aware of what does the CPU actually have to do to perform the operation you're asking it to perform? So, you know, what is actually going on under the covers, and it's really about understanding what is the hardware really doing, how the CPU caches actually work, how is data shared between threads in different cores. You don't need to know a lot of it in depth, but you need to be somewhat familiar, you know, what's going on, because these are the sorts of things which allow you to decide whether to use one approach or another to achieve to improve the performance. The reality is there's also a lot of trial and error. So knowing testing methodologies, how do you write a good benchmark, a reliable benchmark that you can use to inform yourself as to which is a better alternative way of doing things. And then you can use mechanical sympathy to say, well, what's probably going to help here, and try out different alternatives. So I think that they're the two combinations to start with. Again, Martin Thompson has a blog about it. He's called it that. You see a lot of discussion there as to some of the more low-level technical details. Martin does some good talks which make it that sort of information accessible. But again, since you're using Java, you're isolated from a lot of that stuff. So you don't necessarily you can't exploit it to the same degree you can in other languages, but it is still worth having some idea as to what exactly is going on.
Perfect. Alf, I have seen your question. His question, Peter, was again, any resources for learning. So what I'll do, I'll post some of the links that have been posted in this chat with this video as well, so people can buy the books or log on to the resources. Next question. Do you think the Foreign Memory Access API is going to help writing low latency Java systems in the future?
Yeah, so a lot of what they're trying to do is to create maintainable replacements for unsafe. So they're essentially trying to make it the API is secure, so that you can still do you can write secure programs that can't just step out of what the program's supposed to be doing, and also have a stable public API. But in reality, I haven't seen them actually provide any functionality that you can't currently do with unsafe. It's just that it's not supported. Yes, I've seen prototypes where they could support a new functionality. One of the interesting ones is XMM instructions. So having a 128 bit integer type and having proper support so that it gets turned into machine code, efficient machine code instructions. But there's sorts of things that start to do so well. You couldn't actually do that with unsafe today. Is those kinds of operations. But most of what they've been doing though is really about providing the functionality that unsafe is useful, but without the maintainability concerns.
Perfect. Next question. What do you think about the Shenandoah collector for the low latency applications?
So that I believe the main objective there is to have reasonable latency delays when you have a very large heap. So most of the older collectors did a good job up to about 32 gigabytes, depending on your use case. Certainly they did a good job up to 4 gigabytes, but 32 gigabytes, they did a reasonable job. And in some cases, they did a very good job even up to hundreds of gigabytes, but it was by no means certain. It depended on your use case as to whether that was practical or not. Whereas Shenandoah has at least the claim that you're much more likely to be able to handle hundreds of gigabytes and still get good performance, consistent performance. For low latency trading, we take a different approach, which is that we we try and put most of the data off heap. And so we get very consistent latencies. And by having most of the data off heap, we also have very little garbage created. So it's practical to create trading systems which produce less than a gigabyte an hour of garbage. And with a 24 gig Eden size, you can actually run for an entire day without a minor collection. At that point, your choice of garbage collector isn't actually quite so important. But that doesn't mean you can't necessarily run all your systems like that. Particularly things like gateways, web servers, strategy engines, which are written by maybe by quants rather than low-level Java developers. They all end up having to be systems that will create quite a bit of garbage, and so you have to come up with a strategy for managing those. And I think Shenandoah has real potential to particularly support large heap sizes efficiently.
Perfect. Thanks, Peter. A few more questions. So sorry for keeping you so long. Next question is, what is the best way to manage objects off heap?
Keep the life cycle very simple. So that's one of the things that we've done is to, it works well when you make the life cycle very simple. The reason being is that if you have objects off heap, then you're essentially having to write your own garbage collector. And then it gets to the point, well, when does it make sense to write your own garbage collector rather than use the one that's built in? And because they're not easy to write, they take years of testing, and it's really difficult to get a garbage collector correct and efficient and handle a variety of cases. So when does it make sense to make it off heap and do it yourself? And the answer is when it's super simple. So for example, in the case of Q, as I mentioned, it's an event source where you only ever write to the end. So data is only ever added to the end. It's never deleted. You never need to recycle it. That makes your life cycle very simple. So simple that writing your own collector as such is practical. And in fact, what we do there is we roll the files, and eventually you delete the files. That's the collection. When the files have been, the roles have been around long enough, you delete them en masse. Like you essentially delete every event in that file, and that's your collection. Right. So it's very simple. That's when it can work for off heap. Once you start getting a little bit complicated in terms of your object management, you start to get to the point where it just isn't worth the headache and the bugs and all the other issues you're going to come up with trying to do your own garbage collection. And you may as well do it on heap.
Perfect. Next question, is Golang suitable for writing low latency code?
I believe so. I don't really have enough experience to say one way or another, but it certainly Go is an exciting language. So newer projects, cooler projects tend to use Go. However, it's sort of a nicer to use than C++. In reality, though, I think most trading firms will tend to use Java or C++, but they do see other languages such as Go come into to get used as well.
Perfect. Patrice, I've seen your question, but just following on from the question just asked Peter, what's the upside to Java as opposed to C++ on low latency systems?
The main upside with low latency Java and low level Java, or sometimes C-like Java, is it works very well with Java. So you can write normal Java on top of it and take all the advantages of the low level Java, but you can debug between them backwards and forwards very easily. So they obviously work very well together because one of them is just a cut down version of Java. When you develop in C++, you can achieve a more consistent latencies, slightly better performance, and a better profile, but it takes a lot more effort. So with what I tend to find is that if you've got a simple problem and you've got any amount of resources, it'll always be faster in C++. But when you come into a more complex problem, and often find in most business use cases, you have limited resources. You don't necessarily have all the expertise that you might want to develop a really good C++ system. You may have changing and shifting requirements so being responsive to new requirements is important. You don't necessarily have enough time to test and profile it to the same extent. And what I've found is that in many projects, with Java, you're more likely to get something that's functionally complete sooner, which then means you've got a bit more time to spend profiling and performance enhancing. You've got a bit more confidence that you can make changes to the performance after the fact, after you've got something that's functionally complete. And in many cases, I've seen projects side by side, one written in C++ and one written in Java, and the Java system was more performant because of the realistic constraints of limited time, limited resources, a specification that's not clear. And in that sort of more realistic environment, you tend to find Java can actually end up being faster, both in time to market as well as performance.
Perfect. What kind of time constraint defines a low latency Java application?
Yeah, so what is low latency tends to depend on context, and it's usually a low latency project is usually they want to go faster than the last existing system. It also means that they care about latencies you can't see. So just running the system and looking to see whether it's quick enough isn't sufficient. So you need to write programs to test the program to make sure that its latency profile is sufficient. And that's one exercise that tends to be is an extra task in a low latency system and then you have to make sure that your benchmarks are suitable and they're not causing the problem and any kind of delays or making your performance look better than it really is because it's unrealistic in some manner. So that's one of the things that characterizes a low latency system is that you're having to write performance tests, automated performance tests to see whether your performance is acceptable or not. And it generally needs to be faster than the previous one. What that precisely is will depend on the actual situation. But it's typically, it might be as high as a second. I think we had last year, someone said that a second was acceptable. And it can be as low as, so a couple of years ago, we had a client who we contractually needed to be under 20 microseconds wire to wire. So from a packet coming in off the network to a packet going out on the network had to be under 20 microseconds 99.9% of the time. So the worst 1 in 1,000 was still under 20 microseconds. And that includes all the hardware, any kind of OS, everything.
Perfect. And just last question, Peter. You mentioned custom hardware. Have you got any experience with this? That is one question. And then following on, considering co-location is a must for trading systems and a lot of exchanges are now cloud-based, i.e. AWS, is it possible to get custom hardware in their data centers?
Well, if you're going with something like AWS, they're giving you more and more options these days in terms of the choices of hardware, whether you have, high performance network cards, SSDs, dedicated machines, your choice of CPU. So AWS is definitely having a lot more options now in terms of actual hardware, but you may find that if latency is really sensitive, you start getting into games that we used to have in the past where, so for example, if you were accessing Reuters, it used to be that you couldn't guarantee where on the network was the fastest way to do the trading. And so some hedge funds would just have machines in a whole variety of data centers, and then each week they would test which one was trading the fastest, and then just not use the other ones. So you may find that with the clouds as well, you may end up having to, if you can't, for example, measure the exact delay or how long the cable is, you may find that there's a competitive advantage to being that little bit closer, which is why a lot of the low latency exchanges, they can tell you precisely how long the cable is to the exchange, because they make it the same for everybody. And so in the data center above the machine will be this long ring of cable, not to reach you, but just to ensure that the cable is the same length for everybody.
Perfect. One more question just sneaked in, if that's all right, Peter.
Yeah, no problem.
What's your favorite IDE?
My favorite idea is IntelliJ. And I use the community edition, even though as a Java champion I can get a license. Just because I just find that things work together better. Eclipse has got plugins to do most of the things that IntelliJ does, but when you start loading up lots of plugins, in my experience, they don't necessarily all work nicely together. Whereas IntelliJ just has better integration, in my opinion. It may not still be the case, but that's just been my experience.
Perfect. What I'll do, everyone, I'll post these questions as well on our meetup page as well, just so everyone's got them in writing. But thanks very much, Peter. That was really interesting. I hope everyone enjoyed. Okay. I'll put Peter's contact details and his website and business, which is Chronicle Software, and a link to it on our forum as well. So if you've got any questions about this or anything further to do with low latency, drop Peter an email directly. And everyone have a nice evening. Thanks for your time.
Thank you, everyone.
Take care. Cheers.
Cheers.